Okay, good morning everybody. So we'll continue from what we were discussing last time. Last time, if you remember, we had discussed about the use case modeling. And in use case modeling, we not only looked at the constructs, UML constructs, but also given a small problem, how do we identify the use cases, represent them, and also produce a text documentation. We said that text documentation, there is no standard format, but then that we gave few templates, 2-3 templates we discussed, and these are quite well accepted, where we identify the mainline scenario, the alternate scenarios, and so on. So today let's look at a very important diagram, which is the interaction diagram required for almost every problem that we want to design. So let's proceed with interaction diagram. We had seen the class diagrams, the use case diagrams, and in the interaction diagram, we represent when a use case is executed, how do the classes interact with each other. Let me repeat that again. Using interaction diagram, we represent when a use case is executed, how do the classes interact among themselves to produce the required behavior for the use case. Obviously, all the different scenarios of the use cases must be represented in the interaction diagram. Let's see how it is done. So, the interaction diagrams, we model a group of objects and how do they produce the behavior required for a use case. It can be easily concluded that we need as many interaction diagrams as there are use cases, because for every use case we will represent through the interaction diagrams how would the classes interact for that use case and produce the required behavior. So, by interaction we mean how do the classes call each other's method in producing the required behavior. Obviously, we need a way to provide time ordering of messages, that is which message was sent by which object to which other object, next what happened, which object sent a message or made a method call to which other class, and so on. And here the diagrams, as you see, are quite sophisticated. We can represent various aspects. For example, we can represent branching, that is decisions that take place based on some decision, some method is called or other method is called based on the outcome of the decision. Iterations, recursion, concurrency, and so on. So, for every use case, there may be several use cases in our use case model. For every use case, we develop a diagram, something like this. So, for this diagram, the borrow book use case, what classes collaborate and what kind of methods they exchange among each other and in what order. So, that is what we represent. Let us see the syntax, and the end of our discussion we should be able to, given a problem description and a use case model, we should be able to develop the interaction model for that. The syntax is as follows. We draw the objects. Please note it, these are not classes. We show the objects at the top of the chart, the sequence diagram, and the objects are boxes, and then we show the existence of the object through a dashed line called as a lifeline, and then when an object gets a method call, its method is called, it becomes active, and we show this as a rectangle on its lifeline. The method calls or messages are shown as arrows, and we can also show the parameters of a method call and also control information based on which the method would get called or not. Before UML 2.0, the syntax was substantially different, because we might encounter UML, the diagrams before UML 2.0. Let's see the syntax, and we'll also see the syntax of UML 2.0. So in UML 1.x, we were able to represent iteration or repeated method call through a star placed on some condition, or if there are no condition, we just say that for all objects and so on. And an object can call its own method, and that we call as self delegation. So a message can be sent to itself, we can represent that, loops and conditionals. And as I was saying, the UML2 is a new notation called as interaction frames. We will see what are the interaction frames and how to represent this. In UML 1.x, the conditions are represented through square brackets, and iteration we had already seen the star, and this means that a message is sent many times, or a method is called many times, possibly to multiple receiver objects. So these are the elements of a interaction diagram. The sequence diagram, actually there are two types of interaction diagram, the sequence diagram and the collaboration diagram. So we are first examining the sequence diagram, subsequently look at the collaboration diagram. So the objects are placed at the top of the diagram. The objects are basically rectangle, and just see here, this is the name of the object, book, and this is an instance of the book class. So that is the syntax here. This is the same as a class notation. Book is the name of the class, and book colon book. So the first one represents the object ID, and the second one represents the class. But sometimes we also represent just colon and the class name. What really it means is that it holds for any object. If we want to specify a specific object, mention it here. Otherwise, if we don't mention it, holds for any object of that class. The messages are sent to the object, or method calls are invoked on the object equivalently, and that is represented by a arrow. There can be self methods, and this is the condition notation, and the rectangle on the lifeline, the dotted one is the lifeline, and the rectangle on the dotted arrow, the lifeline, is the activation. The diagram is read from the top to the bottom on the y axis. First, the borrow book, the borrow method is called on the member with book as the parameter. If you can borrow book, the can borrow book method is called, and if it returns OK, the borrow member method is called on the book object. The can borrow is a self message, and then if the OK condition holds, then only this invocation occurs, otherwise this method invocation does not. And once the book object is invoked with the borrow member parameter, it invokes the set taken the member and the book copy. So the book copy is updated. So once the borrow book is invoked in the member, and can borrow possibly has not exceeded the number of books can borrow. If it has exceeded number of books can borrow 5 or something, then this method will not be invoked and the member cannot borrow any book. But if the member can borrow, then the borrow method of the book is called, and the book updates the member record on the book copy. We can also show mutually exclusive messages by using the conditionals. Flag is true, this method is called on class B. Flag is false, we invoke the message3 method on the class C. So that's how we represent message invocations on different classes. And the message call between different classes has 2-3 different types of arrows. One is the arrow with a solid head here, and this is the normal invocation, which is the synchronous invocation. That's what we are showing, that for controller object of controller class, a method invocation which is synchronous invocation, as we if you remember, a synchronous invocation is one where after the method call, the calling object waits. In a synchronous method invocation, which is like normal method call, the calling object waits until it completes execution. On the other hand, we might have asynchronous method calls. In asynchronous method calls, it just calls some object but does not wait for it. We will see what's its use. The return value sometimes is represented by a dotted arrow, and most of the time the return value is not represented. It is obvious. When you make a method call to the object, you show the method call, but the return values are not represented usually. Only when it returns some variable that we want to use elsewhere and so on, we show the return arrow and write the variable that's returned. Otherwise, normally most of the diagrams, once a method call occurs, we assume that it after some time it will complete. We don't show the explicit return arrow. So, as I was saying, that the return arrow is optional. Only when there is a variable that is returned, we mention it here. Maybe this variable is used elsewhere in the diagram, and that's the reason we show this. Otherwise, we normally omit of a method call. And the rectangle, as we said, is activation, and as long as the object is active waiting for this, it remains a rectangle. Once it completes, then the rectangle stops on the lifeline. But then we also should know the syntax for object creation and destruction. Object creation, typically we call a method new or create, and once the method new is called on an object, it is created. But then you see here, it does not appear at the top of the diagram. A created object, a object that is created as part of a use case execution, is not present at the top of the diagram because it gets created after the use case has started. The point at which it is created, we show it there, its lifeline starts from there, and sometimes we might like to delete an object, and that we represent as a cross on its lifeline. So, if we cross the lifeline, then we say that the object is destroyed, ceases to exist. But just asking out of curiosity, in Java, how do we destroy an object? We know how to create an object or a new call and so on. But how is object destroyed in Java? Actually, if you remember, Java doesn't explicitly delete objects. We don't have any method call like C++, destructor or something. We don't have any method call to delete object. So, the only way objects are deleted is if they fall out of scope, they are garbage compiled and automatically deleted by the runtime, the Java runtime. But then how do you make it out of scope? Out of scope means we can no more access the object ID. One way is that you assign null to the object, so its ID is lost, or it just goes out of a block where it was created. So, as we are saying that the activation is shown as a rectangle on its lifeline. You can have nested calls. So, the once it is active, it might call itself or other objects might call itself. Then we show nesting here. We say that an object is active when the object is either running its code or is on the stack waiting for some other method it has called to finish. So, we read the diagram, an interaction diagram, from the top to the bottom, that is the sequence, and this occurs first and this is the next and so on. So, just to repeat the different terminology here, the dotted line is the lifeline. We annotate the method invocation or message arrows with the message name, and the activation is shown as a rectangle. So, it is read from top to bottom, This is the sequence in which the objects react. Was this one invokes a method here, and this invokes a method on itself, and then it invokes a method here, payment, and so on. This is another example. So this class waits until the invocation that it made completes. But one thing is that very nice thing about this diagram is that when we draw this diagram, it also implies that this method, add course method, must be supported by the manager class. Let me repeat that. An invocation of the add course on the manager object of manager class implies that the add course is a method of the manager class. Most of the case tools, as you draw this diagram, they would populate the corresponding class diagram, the class representation of the object with the corresponding method name. The add course must be supported by the manager class so that it can be called, and that implication is automatically handled by most case tools, where as soon as you draw this diagram, add course will get populated on the class, the add course method. So this is another example sequence diagram. We will not spend time here. We will look at a few other syntax, and then we will see, given a problem description, how do we go about developing the sequence diagram. As you might have already guessed, this diagram is a very important part of any design. Once you have done the preliminary class design, you need to do the interaction modeling, and the interaction modeling will tell that what would be the methods for that class. The initial design is called as domain modeling, where we will identify the classes, and we may not even identify completely all the set of classes and their relations. They come out when we draw this diagram if we have missed any class or any relation among classes. And not only that, this diagram also helps allocate methods to the classes. So it is a very important diagram. So as I was saying that we might have create or new and so on, and this arrow is annotated, so stereotyped with the create message, and it creates this object. Similarly, destroy, you might annotate this dotted arrow here, destroy, but then normally we do not go into modeling when an object is actually destroyed and so on. Here the idea is to just understand how they call each other's method and so on. Unless there is explicit destroy as part of the use case, we do not show when an object is destroyed, unless the memory management, etc., those are crucial things need to be understood for the use case execution. So as we were saying that before UML 2.0, in UML 1.x, iteration was shown as a star on the corresponding method call. Let us try to do a small problem. Let us try to develop the sequence diagram for this travel portal. Small description of the travel portal is given here, and we want to develop the interaction diagram for the plan travel use case. Let me repeat that. We have a description of the travel portal given here, and we want to develop the use case diagram for the plan travel use case. Let us read through. A user can use a travel portal to plan travel, and when the user presses the plan button on the travel portal, a travel agent applet appears in the window. And once the user enters the source and destination, the travel agent applet computes the route and displays the itinerary. The travel agent widget gets destroyed and disappears after the display of the itinerary. The use case is plan travel, and then first the user presses the plan button, and then an applet gets created, and this applet will have field to enter source and destination, and the user would enter the source and destination. At this, the travel agent applet will compute the route and display the itinerary. Once the user sees this, the travel widget gets destroyed and disappears. So how do we draw this? Obviously, we have to identify what are the classes that are taking part in this use case execution and what are the methods they are exchanging and also in what order. So the client is the one who is invoking the travel agent, and the travel agent applet gets created. Okay, the client is the application, actually client application. This is the on the browser, the client application. The user is here. We don't most of the time show the user, but then we can even show the user here. So the user presses the plan button on the client or makes the plan method call on the client application, and the client application creates the travel agent applet, and the travel agent applet, the client calls set itinerary, and then it calculates the route and displays, and just see that the display is implicit here. We don't draw display here explicit arrows, and at the end of this it gets destroyed, and we show the end of the lifeline here with a cross. There is another quiz here. Let's look at a small problem description and try to develop the sequence diagram for a use case. For every use case, this problem, the RTO office automation, might have several use cases, and for every use case we will have to develop a sequence diagram, and I have written down here the description of one use case. Let's read through the description. A clerk in the RTO office uses a traffic violation application to find the details of any traffic violation by entering the violation ID. So as it says that the clerk would enter violation ID to get the details of the traffic violation. The clerk first presses the view button in the dialog box of the application. The request is conveyed to the controller object. The controller object asks for violation ID. Once the clerk enters the violation ID, the controller queries the database proxy, the DB proxy, using the ID. Based on the response received from the DB proxy, the controller creates a violation object and passes it to the dialog box for display by calling its display method. So this is the solution to this quiz. The different classes are, if you read through the text, you will see that the different classes are the violation dialog, an instance of violation dialog, the violation controller, the violation database proxy, and then traffic violation. So the proxy actually takes care of invoking the method on the database. So not showing the database itself here, or just having the proxy here. The clerk invokes the lookup method here, or presses a button here called as lookup, and once he presses on the dialog makes a call to the controller view button, and once that is called, the controller requests for get ID, and once the ID is obtained, we are not showing the return path for this call, and once the ID is obtained, it calls the get violation on the database proxy. The database gets the ID, and then it creates a traffic violation object, and the details of that is displayed here. So we are showing the return arrow here because V is the object that it returns, and it is displaying V. Display may be a pseudo method, it may be just a return here, and it gets called by the violation dialog. Now let's look at another quiz. I am showing many examples because if we practice through these examples, then we would not only know the syntax of the interaction diagrams, but also know, given a problem description, how do we create the interaction diagram. And normally in classroom, just display the problem and request the students to work this out, and then we invite them to draw it on the board and request the other students to suggest corrections, and finally we display the answer and compare with the answer that is obtained from the students. Now let's read through here. A print server is an active object. An active object, as we discussed in the beginning of our lecture, we said that an active object is like a server. It is always active, and it just waits for method calls, and then once it gets some request, a method call, then it processes, but the calling method does not wait for it. So, the print server is an active object. The client application sends jobs to the print server and it just takes them, and they don't have to wait for print to get over. So, that is the meaning of the active object. And as soon as a print server gets a request to print something, it enqueues the object on a queue object. It creates a queue object and enqueues it. The job server takes up job one by one from the queue. So, it retrieves from the queue and then each time it prints one, and as soon as that completes, it takes up the next job. So, it prints by sending them to the printer proxy. Now, how do we draw the interaction diagram for this, the sequence diagram? The print server is an active object, and we had seen in the beginning that an active class is just like an ordinary class excepting of the parallel borders. And this active class has its life, the rectangle appears all through because it is active all the time. And just see the message type shown here, it is a half arrow here. The half arrow is asynchronous object. Normally to a active object, you just send it and the client application does not wait for it. It continues with its other activities, and the print server takes the request and sometime it might process and it might report the done status after it is done. But the client does not wait for this. That is the indication by this half arrow. So, once the print server gets the job, it calls the enqueue job on the queue. See here, we did not discuss it so far, but this is the UML2 syntax where we show the looping or the iteration using a frame called as a loop frame. So, what this frame indicates is that all these things repeat until the condition here turns to be false. As long as the queue is not empty is true, that is the condition mentioned in this frame. This is the name of the frame is the loop frame, and then queue not empty is the condition. As long as this condition holds, these ones are repeated. So, it calls here on the queue to dequeue the job comes here, and there is a job, prints it by calling the printer proxy, calling the print method of the printer proxy, and then it might return the status and then finally the job done. And as this diagram is drawn, the case tool will populate these ones. On the printer server, we will have the method print, and on the queue we will have enqueue, dequeue, and on the printer proxy we will have the, in this solution we know not only how to draw a diagram representing the interacting objects from looking at the text description of the problem, but also we could see the UML 2.0 syntax. We will see the syntax in slightly more detail as we proceed the subsequent slides. So, this is called as the guard or the conditional. Based on whether it is true, it will get invoked, otherwise the invocation will not occur. So, this is the new thing in the UML 2.0 in interaction diagram called as a frame. A frame is a rectangle. Name of the frame appears here. The identifier can be a loop frame, or it can be a name of the use case for which it is drawn, the order process. Earlier in UML 1.x and so on, we could only represent the name of the interaction diagram by writing at the bottom and so on. But here there is a specific place where we write the name of the sequence diagram, and then we, as in UML 1.x, we draw the names of the participating objects, and similar are messages, but then we have these loop frames and so on. So, this is the sequence diagram for the order use case, and then inside here is this loop frame, and this loop frame will continue to add item to the cart, and then from cart a reserve item may be called here and keeps on adding items. We are not shown any condition here. So, this is the syntax for showing a frame. So, this is the sample, and it okay, this is the operator. We write what sort of frame is this, maybe a loop, maybe an alternate, and so on. And then we write the operand here, which may be a condition. So, the first one we see here is a okay. So, we just write here, this is the general syntax. We will see the specific ones here. We just write what operator it corresponds to. We might write a guard condition here, and then we throw these dotted lines, we might split into different parts. So, depending on the guard values, these parts will get executed. So, that is the general syntax. Now, let us look at the exact specific syntax. The different operators that are supported are alt. Alt is if it is true, it will execute, otherwise not. Loop, okay, sorry, just a small correction. Opt is the one which will execute if the guard is true, but alt is it gives two alternatives. One of the alternative will get executed depending on the condition. So, alt we will have two alternate actions, one depending on whether alt is true or alt is sorry, the condition is true or false, and these two will be shown through dotted lines. We will see examples of that. And then parallel, critical region, this will normally not applicable until you are developing some embedded applications and so on. We will omit this from our discussion. We will look at alt, loop, and opt operators. Actually, there are many more in the UML syntax. Reference, interrupt by break, assertion, and so on. We will not really look at that. In the alt, as I was saying, that there are two alternate actions that may take place depending on what is the outcome of the condition. If the new customer is yes, then it will call the create customer info on the order. If it is not a new customer, then it will get customer info. The loop will have the loop operator written here and also the conditional. As long as the conditional is true, the loop will continue. So, there are more elements. So, more is set here, this value. So, it is calling process item on the inventory, and has item calls on some iterator, and then if it returns more, then it continues until the more becomes false. So, this represents the iterator pattern, where a iterator object gets created as part of looping. We are really running short of time. Maybe we will not be able to look at the different patterns, but the iterator pattern is one of the very important pattern which has got assimilated into programming languages such as Java. So, we can even nest different frames. So, this is the optional frame where this takes place, set of actions take place depending on what is the outcome of this condition. The loop may not even be executed if this is false. Now, we said that the sequence diagram helps a case tool, or even to manually we can generate some code. If the diagram is like this, that the object of employee class calls a method of the employee DB class, then we said that employee DB class must have a method called as getEmployee. That same method name must be a method in this class, and it must take an emp id as its argument and returns an employee. This is another example. The user is invoking the make square here, and then it is calling the new method on the square. So, the SEP factory must support a make square. So, the make square method is a public method supported by the SEP factory class, and not only that, we can also infer that it is invoking new on the square. It is invoking new on the square object, square class. Now, this is a quiz. We also displayed the answer here. We are saying that given this diagram, sequence diagram, what code will be generated for this? And we want the code for the tree map. As you can see here, the tree map needs to support the clear method. For anybody to call it, send a clear message, must support the clear method. And as part of the clear method, it will destroy a tree node. So, this is the public class tree map, and it has a tree node ID here, and whenever a clear is called, it is just setting t equal to null, and the object here is getting out of scope and getting automatically destroyed by the garbage collector. This is another quiz. So, here we have this diagram given to us, and the controller, on this the purchase method is invoked. So, that means it must support the purchase method. Thus, once it is invoked, the purchase method on the controller, it invokes the new on the purchase. It creates a purchase object, and then it invokes the buy grocery, and finally it calls the create of the payment with the cash tender. So, we want to create the code for the controller class. So, controller class has the purchase method it supports, and then it creates the purchase object, and then it creates the payment. Sorry. So, it creates the payment object, and on the on the purchase object, it calls the buy grocery. So, how does it call the buy grocery on the purchase object? Calls my purchase, which was created here, my purchase dot buy grocery. On a case tool, when you create the diagram, a sequence diagram, the methods will automatically be populated, the set ID, set name, set age, etc. But also template code is generated. Now, let us see for this case tool, what is the code for this will look like. So, this is the code here. So, this is the class register controller. So, register controller supports the register method, and once the method is called, it calls several other methods. First it creates the account object, and then on that object it calls several methods, and finally calls the add account and the account list, and then it completes. So the same code has appeared here. The code for that has appeared here in the case tool. See here, register controller supports the register method, and as part of that it creates the account. The ID of the account object is account, and then it calls the methods there: set ID, set name, set age, and so on. Most of the case tools support this kind of code generation based on the sequence diagram. Now let's look at another example of the sequence diagram. The compute price use case is invoked in the context of a specific order to calculate the price of the order. All the line items are examined to determine their prices, which are based on the pricing rules of the lines, and then the overall discount is computed, which is based on rules tied to the customer. So specific customers will get specific discounts. So once we have got such a description, the first thing is to identify what are the classes that are participating, and then what methods they are calling and in what sequence. So if you read through this, you will see that there is a specific order based on which the compute price is invoked, and then the line items are examined to determine their prices on the order. So order, the compute price use case is invoked in the context of a specific order. So order is a parameter for the compute price, that is the context, and then for the order all line items are examined to determine their price. So determine price is a method for the order class, and for all line items, that is a loop here, and based on that the pricing rules are applied for the products, and the overall discount is computed. So if you draw that here, it appears like this, that the customer calls the calculate price, and then the order object, it knows specific order object, and then the order object ID, it invokes the calculate price, and on this there is a loop here for every line item. So for the corresponding line item, calls the get quantity, get product, and get pricing details for the product, computes the discount information by first getting the what is the discount to be applied to the customer. So that calls the get discount information, what sort of discount to, and then it computes the discount. We can have other examples here. Draw sequence diagram to represent message exchanges when the print game money method of the class is invoked. So we have given a code here and asking you to compute to draw the sequence diagram, to develop the sequence model based on the classes. So there are two classes here, ticket and game, and it says that develop the sequence diagram when the print game money method of the game class is called. As you can see here, once it is called, it loops here. So there is a looping here, and then it calls ticket.getPrice. So it invokes the get price of ticket on the ticket class, and then computes the total. So if we represent it here, it would appear like this, that it loops for all tickets, it gets the price of the ticket. We have some exercises here written down. Please try them. If you have difficulty, you can discuss, or you can send me we have answers also displayed here, so that you can check your. There are further exercises. Please read through the exercise and develop the sequence diagram. So there is part of that exercise here. Now the collaboration diagram is also another interaction diagram. Normally we develop the sequence diagram as the interaction diagram, and based on the sequence diagram, the collaboration diagram can be automatically generated based on a button click on the case tool. It contains as much information as the sequence diagram, but then you will ask why do we need the collaboration diagram? The answer to that is that some aspects of the software are obvious in the collaboration diagram and not so obvious in the sequence diagram. Given a sequence diagram, this collaboration diagram, it does not show the timeline, but then it numbers the message exchanges. So, first this occurs, this one calls here, second this one calls here, third this one calls here, and so on. So, one thing that is obvious on this diagram is that what is the relationship among classes, which class is related to which class, and it calls what methods. It is obvious by looking at this diagram, which is not so obvious, like whether a class is related to another class. You would have to really examine the diagram, sequence diagram, but here it is obvious. So, that is the utility of this diagram, and as I said, we do not develop it separately, it is done automatically from the sequence diagram by a button push. So, given this interaction diagram, this is the corresponding collaboration diagram. Given this sequence diagram, this is the collaboration diagram, and as you see that attach method is invoked on the stock quote publisher by the stock quote subscriber, and this is the first message. We saw that here by number 1, attach is called on the stock quote subscriber by the stock quote subscriber to the stock quote publisher. So, this is another example as you can of a collaboration diagram. As you can see that which class exchanges how much messages with another class and whether it exchanges any message or not is obvious here. For example, book is not directly related to library member, they are not associated, but indirectly associated. This is another example. We have this sequence diagram and we want to generate the code for class B. The class B should support which methods? It should support do A, and then it should invoke which methods? Should invoke create and do B. So, that is what it shows. Class B supports do A method, and in turn it creates the new C and then invokes the do B on the A. So, we have so far seen class diagram, use case diagram and sequence diagram. Now, let us for the next hour that we have, we will see that what is the method by which we will generate these diagrams for a given arbitrary problem description. We might have a page or two of write up, text write up about a problem, and we would like to develop the use case diagram, the class diagram, the sequence diagram, and as soon as we draw the sequence diagram, the method calls will get populated on the corresponding classes, and then it becomes easy to, and that also generates a code skeleton, and based on that we can write the complete code. So, we will just take a small 5-minute break now, and we will come back here in 5 minutes and we will continue discussing about the object oriented analysis and design methodology, which will make use of the UML diagrams and help us come to the code from a problem description. Okay. So, we will continue from where we had left. We are going to discuss about a object oriented analysis and design methodology based on the diagrams that we discussed, which were the class diagram, use case diagram and the sequence diagram. Even though at the start of our lecture we had planned to discuss about the state chart model, how code is generated from there, the syntax, and how to develop a state chart diagram, we are unable to do that in the given time allocated. So, let us proceed, and as in most of the design processes, the process that we are going to discuss it is an initial analysis is done, object oriented analysis, and subsequently we will refine this into a design model. The approach that we are going to discuss is largely based on the Lerman's approach. So, in almost every object oriented design process, we do an analysis followed by a design, OOA followed by a OOD. Here the starting point is a text description of the problem, and we develop an analysis model, and then based on the analysis model we develop the design model. And both analysis model and design model we use the UML syntax, but then the specific constructs etc. that we use may be slightly different in the analysis and the design model. So, if we diagrammatically represent what we are just now said, initially we do a analysis model which is iterative. We will go on refining the analysis model, and at the end of the analysis model we would have got the domain model and the use case model done. And then we do the object oriented design and object oriented programming. In object oriented design we do the sequence diagram and so on, and then we generate the code from there, code skeleton, and whatever is not generated from the diagrams we write those. But then just asking you this question, that how is analysis different from the design? So, the question is that how is OOA any different from OOD? So, that is the quiz, that how does OOA differ from OOD? The answer is that in analysis we just look at the text description or the requirements and we just model that what is given. It is just a modeling of the requirements. Of course, we might elaborate here in terms of which are the classes involved and so on. But then in a design we take the analysis model and we look at the implementation constraints, and then we refine this model. So, analysis is done based on just looking at the problem space, whereas design we have the implementation in mind, whether we are using a database etc. So, we look at the implementation constraints and refine the analysis into a design. Now, let us see how do we go about. So, these are the different diagrams that we use as part of our design process. The initial part is the analysis and followed by the design, and all through we maintain a glossary where the specific terms that we incorporate into a design are explained here in the glossary. All through new terms are introduced, maybe method names, maybe attribute names, class names, state names and so on. All these are maintained in the glossary. So, to start with, take the SRS document or the text description, and also for large problems we need the user interface prototype. Last time we had said that for developing a use case model for a large problem, non-trivial problem, we need the GUI prototype, because the GUI prototype tells us that what will be the methods sorry, what will be the use cases and how will the use cases be organized into packages. We had taken the example of a word processing software. We said that what are the menu items available, those are the packages, and each package contains the use cases that appear on the drop down once you select the package, view, create, etc. And then we take the GUI prototype and the SRS document. Based on this, we develop the use case diagram. And once we have done the use case diagram, based on the SRS document and the use case diagram, we will get the domain model. The domain model is the initial class structure based on examining the problem description. The class structure that is obvious from the problem description, that we call as the domain model. And then we look at the use case diagram and the domain model and get the interaction diagrams. Sequence diagram, as we said, can be developed first, and based on the sequence diagram, the class diagram is populated with the method names, and we might also change the interaction diagram based on new classes introduced here, or classes we might combine them together. If a class doesn't have enough method, we'll combine them. Large classes having large number of methods, will split them, and based on that we'll refine the interaction diagram. And finally, the code is skeleton is generated from here, and we might write the missing parts. So that's the typical way in object-oriented development takes place. That is also shown in the rational unified process. As you can see here, that the analysis and then the design occurs almost throughout, starting from inception, elaboration, construction, and transition. And at the same time, the implementation takes place and the deployment peaks towards the end. So these are the different diagrams that are involved in the design process, the object-oriented design process. These are the diagrams. Initially, we'll have the use case model, the activity diagram, and so on. And during the design process, okay, we'll have the state diagram, activity diagram, class diagram, object diagram, sequence diagram, collaboration diagram. And during the coding, we'll come up with the package diagram, component diagrams, and deployment diagrams. Just an indicative use of the diagrams in different stages of development. So the crux of our development process, design process, is that we will somehow come up with the use case model based on analysis of the requirements and the GUI prototype. And based on the use case model, we will come up with the domain model. And the back arrows here show any refinements may occur on the use case model based on the domain model that we construct. And then based on the domain model, we will develop the interaction diagrams which capture the dynamic behavior of the object. And all through we have this glossary which defines the terms. Now we had seen, given a small text description, how to develop the use cases. To identify what are the high level requirements, represent them as ellipse, and decomposition of the use cases. We had seen that earlier. Let's not spend time on that. We'll spend time on this one, which is new, we did not so far discuss. How do we develop the domain model? So we have the text description available to us and also the use case diagram, and we are trying to develop the domain model. The domain model, as we said, we are trying to model the different objects or the classes that are obvious from the problem description, and the domain model gets refined into the class diagram as the implementation proceeds. So, we have the design and then coding. The domain model is the one which gets refined, and there are three types of, okay, there is some chat request, okay, okay, now. Okay. So, the domain modeling, we look at the problem description and we try to identify three main types of objects. We look for three main types of objects from the problem description. One is called as the boundary object, one is called as the entity object, and the last one is called as the controller object. So, we have a problem description given, and the objects possibly which that can be identified fall into three categories, and for each category we would have to identify what are the objects that we should get from the problem description. In almost every case tool, we have actually different stereotypes corresponding to these three classes, three categories of classes. If these three categories, this symbol stands for a boundary class, supported symbol supported in most case tools, boundary class representation, a controller class representation, and the entity class representation. If we do not have these symbols available in a case tool, we might use stereotypes. So, a normal class will stereotype with boundary to indicate that it is a boundary class, a control class, or an entity class. So, every problem that we solve will have classes of these three types. Now, let us see what are these three types and how do we get these classes. Okay, so this diagram just shows that how the design model may differ from a domain model. In domain model, we just have the class names and so on available to us. Here we have the method names here. So, this is we call as the implementation perspective, that we have to have these methods supported here and then the code for that and so on. So, let us look at these three types of classes that are present in every solution for a problem. The first one is the easiest one. These are called as the boundary objects. The boundary objects are actually the user interface objects, typically GUI. It might have been appropriate to call these as interface objects or GUI objects, but then since interface is a term in Java, UML and so on, it was avoided, and boundary object is the name that is given to this. So, this basically represent screens, menus, forms, dialogues and so on. And all these boundary objects, they are concerned with the input and output, collecting input from the user, maybe validating if a character input is to be obtained and the user has given a integer input, maybe it will request the user to give a character input, and similarly it may display. So, the boundary objects do not do any processing activity other than just validating the input and formatting the output. They are responsible for collecting user's response and giving response to the user. The entity objects, these are the objects which store information for a long period of time. For example, in the library case, the different books, the book register, the member register and so on are all entity objects. Once created, they last for quite some time until they are explicitly destroyed. And the main responsibility of these objects is to store items. So they store data. We can query data from this, and maybe some simple functions like sorting data, searching data, and so on. And the entity objects are the one which appear as nouns in the problem description. We will see how to identify the entity objects. The third last category of objects is the controller objects. These are the ones which actually get the work done for a use case by coordinating the boundary and the entity objects. When a user invokes a use case, that is reported to the control object, and the controller object, it knows what to be done. The controller object knows what needs to be done, which classes need to be invoked, in what sequence, etc. Or in other words, they know the business logic, that if the book renew method is called, the controller object will know that first whether the book has not been reserved by somebody will be checked, whether the membership is valid will be checked for the period for which the book is being issued, and then the book object has to be updated with the new date. The members record will also have to be updated. So these are the different method calls that the controller objects will have to do, and finally call the boundary to display. So it knows the business logic that given a use case, what all action needs to be take place, and it will get those actions done by coordinating or requesting the entity and the boundary objects. So if we look at definition of a controller class, it coordinates, sequences, transacts, or otherwise controls the other objects. And in the small MVC mechanism, model view controller mechanism, these are called as the controllers. So in the literature you will see that in books, different books and articles, you will see that sometimes these are called as controller objects and sometimes control objects. If we diagrammatically view what a controller object does, once the user gives input or invokes a use case, equivalently you can say that a user has invoked a use case through a boundary. The boundary does not do processing other than validating the input, and it just passes the same thing to the controller. The controller, once it knows that the user has invoked a use case, it knows that which entity object has to be invoked, and then each entity may invoke other entities, and finally the controller has completed the use case execution, has got it completed through the actions of the entity classes, and then it reports the result through another boundary object. So that's the way it normally every use case is implemented. So this is the sequence diagram. Once we have the domain model, we'll write the classes of the domain model and then draw the sequence diagram, and then we'll have the method names appear in the classes identified in the domain model. But what about boundary objects? How do we identify them given a problem description? It is very straightforward. We look at the use case diagram, and every use case actor pair will have a boundary. So every use case actor pair will have a boundary. So how many boundary objects will be there? There is a boundary object register customer boundary, clerk and register customer boundary, sales clerk and register sales boundary, and managers select winners boundary. So what it really means is that the customer will interact with the system through the register customer boundary for this specific use case, and this boundary will invoke the controller for this, whereas the clerk will have a separate boundary interface, a boundary through which it will interact with the controller. Now, how do we identify the controller objects? So, boundary objects, we found that it was straightforward. Looking at the use case diagram, we know that as many actor use case pairs are there, that many boundary objects we need. The controller objects are also easy to identify. We add one controller class for every use case. So, the controller class, once the user invokes a use case, the controller class gets the control, it knows how to realize the behavior of the use case by coordinating the activities of several entity classes. So, it will invoke methods on those entity classes, and the entity classes also may invoke methods among themselves to satisfy the controller's request. And finally, as the use case work is done, it will report it on a boundary. So, every use case requires a controller, or in other words, our rule is straightforward: add one controller class for every use case. We saw that boundary objects and controller objects are really mechanically and very simply identified. But what about entity objects? Entity objects are not that straightforward. These are actually have to be identified from the text description. We read through the description, the requirements document, and we find out all nouns. So, this is called noun analysis for entity object identification. We identify all nouns, and then the nouns that describe the user are excluded. Passive verbs are also excluded, and also those nouns which are neither users nor passive verbs, but we cannot associate any data with them, we also exclude them. They are just attributes. If there is a noun with which we cannot associate data or methods, we cannot associate methods, we don't make them classes. Similarly, those with which we cannot associate methods, we don't make them classes. And also, once we identify the nouns based on this, we might need to make some of the nouns which represent the users, user names and so on, we make them classes. These are called as surrogate classes because we need to store some details about these users. For example, library member, even though library member is a user, we need to have also a class inside the software called as library member, because we need to retain the data of the library members, how many books they have taken and so on. When is the membership expiry and so on. For that, we, for some of the objects, users, some of the nouns representing users, we make them as classes. Now let us take an example. So we have a text description, simple text description. for which we will have to identify the entity classes. For the boundary and controller classes, as I mentioned, we need to just look at the use case diagram and we get them very simply. Whereas for the entity classes, we need to do this noun analysis from the text description. And if we do noun analysis for few problems, 5, 7 or 10 problems, we get a understanding, and then by reading through the document, we can easily identify what are the entity objects. We don't have to actually underline the nouns and do the analysis. We can just read through and identify the entities. That's after we gain little bit of experience. Now let's for the first problem, let's read through and then highlight all those are nouns, and then we'll exclude the nouns which cannot be classes. So let's read through. The user is a noun, must be allowed to specify each product is a noun by its primary characteristics, including its name, product number. If the barcode, which is a noun, does not match the product, then an error should be generated to the message window and entered into the error log. The summary report, the noun of all transactions, the noun must be structured as specified in section 7a. So section 7a is also a noun and not highlighted here. We could have also highlighted here. But then, as we mentioned, that all nouns are not really classes. The ones that are users describe the user, with which we cannot associate any data or with which we cannot associate any methods, are not classes. So characteristic, the characteristic is, we cannot associate a method other than get characteristic and set characteristic. So it is an attribute of a product. The product has characteristics and this is attribute. Name is attribute. Product number is attribute, and so on. So we have crossed the user. It cannot be a class, represents a user. Characteristics, product name, barcode, name, these cannot be classes. We can't have meaningful methods associated with them. These are the attributes of this class product, and so on. So let's have a small exercise here. Okay, we'll have the exercise a little later, but then one thing is that the classes typically denote a collection of objects. For example, students, coins, and so on. But then when we name the class, please observe that these are the class names are singular. We don't have a students class or coins class, etc. So the class names are always singular, even though we might have multiple objects created from that class. There is another hint here how to identify the entity objects from the problem description. One is that if we draw a data flow diagram, then these entities typically appear as data stores, and almost every entity class appear as aggregate objects, whether you say books. So there must be a book register which is aggregating the books. Members, these are also aggregate classes. Reserved books, etc. So almost every entity class occurs as aggregate class. The controller, boundary, etc., these are single classes, but here typically we represent them using the aggregate relationship between classes. As an example, sales history consists of many sales records. So typically the entity classes appear like this. They are aggregate classes, and typically the entity classes are stored in a database. So now let's do a very small problem. The tic-tac-toe computer game. We want to read through the problem description and come up with the use case diagram, the use case model, the domain model, and the sequence diagram. And in the domain model, we want to discuss only about entity classes, because the others are quite straightforward. The boundary and controller classes are mechanically identified. So let's read through. A human player and the computer make alternate moves on a 3x3 square. A move consists of marking a previously unmarked square. The user inputs a number between 1 and 9 to mark a square. Whoever is first to place 3 consecutive marks along a straight line on the square wins. So what will be the use case here? Use case is about placing mark. The only activity that the user can do here is to mark a square. So, okay, these are further descriptions of that. So if we draw the use case diagram, it is play move or mark square, any of the names you can give. And there is only one use case, very simple problem. The player invokes the play move use case, and this is the name of the software. Now the next step is to identify the different classes in the domain model. By looking at this use case diagram, you know that there will be one controller class and there will be one boundary class. The player play move boundary and the play move controller. But what about the entity classes? For entity classes, we need to read through the problem document, identify which class stores data and supports some methods, meaningful methods. So if you do that, you will find that board is the only entity class, and board consists of squares. The other things are mechanically identified, the one boundary class, one controller class, and one board class. And the next step would be to look at the text description of the use cases and draw the sequence diagram. In the sequence diagram, we identify what are the classes from the domain model participating, and then what methods they call on each other. But for problems, non-trivial problems, developing the sequence diagram is non-trivial, especially if there are 8, 10 or 20 classes involved in a use case execution. Then to find out which object is invoking which method on the object is a non-trivial task. For simple classes, yes, by looking at the problem description, as long as you understand what takes place in the use case, you can develop the sequence diagram. But for problems having large number of classes and complex interaction among the classes required for a use case execution, it becomes difficult just to read through and develop the sequence diagram, and for that the CRC cards are used. The CRC stands for class responsibility and collaboration card. We'll look at that in the subsequent slide. And these cards are used to assign responsibility to classes. That's basically assigning responsibility essentially means about drawing the sequence diagram, because as long as we know that it supports some method, assign responsibility means identifying what methods it will support, and that basically is about developing the sequence diagram. So as long as there are dozen classes collaborating, dozen subclasses, reading through the problem description and developing the sequence diagram is not very easy, and we use the CRC cards. Initially developed by Ward Cunningham and Kent Beck. And here for every class in the domain model, one index card is prepared, something like a playing card. So on this card, a small card, maybe 3 by 4 inches or something, small cards, and on these cards we write the class name, the class responsibility and collaborating objects. And now let's see how these cards are used. We have created one card for each class in the domain model, and these cards are used by a team to identify the methods for each class, and this systematize the development of the interaction diagram for complex use cases. So as we had discussed, responsibility means the method supported by a class. Collaborator is the class should invoke a method on which other class. So the class on which it invokes a method is called as a collaborator for the execution of the use case. The card would appear like this. We write the name of the class on the top, and for every class in the domain model we have a card like this where the name of the class is written at the top, and then as we carry out the CRC, the team member takes up the CRC card and they identify the names of the methods to be supported, and then as part of this method which other classes, the support of which other classes are needed. Now let's see what does the team members do to develop the method population for the cards. They take up a use case. The team members, maybe 5-7 of them, initially they read through the use case description, identify what are the classes that are involved, and then they distribute the classes among each other. So let's say there are 15 classes that are involved in a use case, and there are 3 members who are doing it, or maybe there are 5 members who are doing it. Then the 5 members will distribute 3 cards among each other. So 3 cards, each will start with 3 cards. Each member will have 3 cards, and then they read through the text description of the use case. So as they read through the text description, they find out that some class needs to do something, and then they debate. They look at the classes they are holding, the card for the CRC cards for the classes, and once an action item comes up. An action item typically appears as verbs on the text description. So as soon as a verb comes, they find out which class should be responsible for doing that action. So each member in the team looks at the cards he is holding, and he may find that his class should do that, and then he writes down, discusses with others, and writes down on the his CRC card. So once the cards are done, sequence diagram is developed, and then based on that the class diagram is automatically developed if a case tool is used, which has the names of the method the class will support and the specific attributes that it should contain. So there are some examples here. We need to read through these examples, work out the use case model first, and then we work out the domain model, and then based on the use case diagram and domain model, we do the sequence diagram. So not really read through, please read through, the slides are given. Please read through and then draw the sequence, the use case diagram first, and then the domain model. The domain model, the boundary and the controller classes are straightforward from the use case diagram, and then the task is to identify the entity classes. And entity classes, the hint is that they typically store data for long time, and then they appear as aggregate objects and are nouns in the problem description. Somewhere they would be appearing as nouns. So this is the problem description. Will not go through it. It's left for you to read time, and you have to develop the use case model, domain model, and sequence diagram. And we have the solution shown here. Use case model, you should get this. That using the software, the customer should be able to register, or even the clerk should be able to register a customer. The sales clerk will register the sales, and the manager will select the winners. And based on the requirement document, you can try to identify the entity classes, and typically they occur as aggregate classes, and from the you can identify sales history aggregates sales records, and the customer register aggregates the customer record. So these are two entity classes. And this is the complete domain model, where you have the boundary classes and the controller classes also added to this. And based on this, you can read through the use case text description and then develop the sequence diagram. Or if there are too many classes, you would have to use the CRC card. So based on this, you should be able to come up with such a sequence diagram. For each use case, we come up with the sequence diagram. There are 3 use cases. So we'll have 3 sequence diagrams. So this is the second sequence diagram for the customer, register customer. And then there is one more use case, which is the register sales. So please try this and compare your answer with the one that is displayed. And sometimes you'll find that a class has very little to do. Very little methods, and that's the time when you decide to add that method to another class and get rid of the class. For example, this controller has very little to do. It just gets the invocation from here, and then based on this just calls here. So it is the responsibility of the register cells is very simple. It just passes on the request from here to here and then from here to here. By itself, it does not do anything else, and therefore we could also remove this and have this directly invoke the history cells history. So whenever there are trivial responsibility for some classes, we might remove that class, and also if there are too much of responsibility of some class, we might split that class into two classes. So those are the refinements. That is the refined sequence diagram for the register cells, and then we would have the class diagram where the methods are populated. You can look at the sequence diagram and ourselves populate the method. If you are using a case tool, it will automatically be done. There are few other problems are given here. Please take that as an exercise and work out, develop the use case, class diagram and sequence diagram. One more problem here, one more here. So please try to work out the solution for this. Okay, one more, 4 of them are there, 5 of them are there. Look at the slides, try to work out. If you are successfully able to work out, you have understood and mastered the design process. Okay, one more. So 6th one, 7th one, 8th one, 9th one. So there are 9 problems that are displayed here because it requires a lot of practice. As you practice through, next time a problem is given, you will just look through the problem for a few minutes and come up with the solution. And with that intention, given 8-9 problems for you to work out. Now let's look at how do you test object oriented programs. Is it the same way as you test procedural programs? Let's see, not really actually. As you see that testing object oriented program is a different ball game compared to testing procedural programs. Now let's see the issues that are involved in testing object oriented programs. The object orientation, as you remember, was introduced to save on effort, come up with good design. And in the initial years when the object orientation was proposed, it was believed that object orientation will substantially reduce testing effort because this is such a good design compared to a procedural one. Encapsulation, polymorphism, abstract classes and so on, and therefore should take less testing because these are good cohesion, coupling is low and so on. Good design should lead to code which are almost good and the small testing effort is required. But in the later years it was realized that not so. Actually it complicates testing. Many new types of bugs can occur here and the testing effort in questions. One is that what is an appropriate unit testing? For unit testing, what do we mean by a unit of an object oriented program? For procedural programs, unit testing means testing a method, a function. For procedural programs, unit testing is basically testing a function. So by that, if we extend it to object orientation, it should have been a method. A method should be a unit of object-oriented testing, but we will see that not really. A method is not a unit of testing. We will see why. And then we will see that the different object-oriented features we said are good: encapsulation, inheritance, polymorphism, dynamic binding, and so on. Do they help or complicate testing? What about the state models of classes? Do they require extra testing? How do we do test coverage analysis and then the integration strategies? A suitable unit of testing for a function is for procedural programs. By same analogy, we should have methods as the basic unit of testing for procedural programs, but then not really, and that is indicated by the Wave-Kerr's anti-composition axiom. So, if we interpret the anti-composition axiom for object orientation, it says that any amount of testing of individual methods can not ensure that a class has been satisfactorily tested. So, the anti-composition axiom says if a class has 10 methods and each method independently we test, do unit testing on these 10 methods, just take one by one method and use our procedural approach and you test each of them, find that they are working satisfactorily, but based on that we cannot say that the class is working satisfactorily. Let us see the reason. There are two reasons actually. One is that individually the classes may be working, the methods may be working fine. We have we have tested each of the methods. But what about the method interactions? Because they are sharing the class attributes, a method independently we saw that it is working fine, but it might be setting some values which are used by another method and it may fail the method. So, individually the methods may be working fine, but their interactions may have problem. The second thing is that each object typically has a state model, each class has a state model associated with it. So, we need to test the methods at each state and the state transitions and so on. So, just testing the methods at any one state of the class is not good enough. So, there are two reasons. One is we need to check the interaction of the methods, then only we can say the class is working fine. We need to also look at the state diagram of the classes, and therefore testing methods in isolation does not achieve much. We need to test at the class level. So, the class is the suitable unit for testing. The unit testing in object orientation is done at the class level. We test the classes. Okay, so as we said that this is based on the Wave-Kerr's anti-composition axiom. So, one thing that we concluded is that our unit testing will be done at the class level, not at the method level. And then what about encapsulation? We said encapsulation is grouping the data and methods together, and also in object orientation we have encapsulation implemented through information hiding. Does that help in testing? Okay, it does not create problems for testing, does not create additional bugs, but then because of this information hiding, it is difficult to look at the internal values of a class, because that is the basic reason for this information hiding, that we can only get the values by method invocation. So, we need to break the encapsulation, and typically we have state reporting methods for classes. and that's not a very big problem actually. So for testing we need state reporting methods by which you can examine the values of variables for classes. What about inheritance? Does it simplify testing? If we have tested a base class thoroughly, can we incrementally test the derived classes? So we know that the attributes and methods in the base class are working fine. Let's say we have tested this class at the unit level. Now we added one more method here. So can we test only that method? No. Retesting of all the inherited methods is required. Now let's see why retesting of the inherited methods is required. We need retesting because of the new context of uses. So the new method that we added, the derived class, may actually cause the existing methods. It might set some values based on which the inherited methods may fail. Can we come up with some examples to show that we just added a method to a base class in the derived class, and the base class methods that were inherited, though they were working fine in the base class, they stopped working correctly in the derived class. So that's a quiz here. Give an example of for which a method works correctly in the base class but ceases to work correctly in the derived class. And the solution for the quiz. So we have this class A where x is taken care by m so that it never exceeds 200. But then we later extended class A B and we had a method m1 which did not examine all this invariant and all that, and it set the value x equal to 1. And then next time m will be invoked, that will fail. There are further examples. So here we had this m calling m2, and m2 was a method here. So it is calling the method here, but then b extends A and also overrides m2. Now when we call m here in the context of class B, it will call the m2 here, not the original m2. Even though unintentional, we overridden m2 here, and because of dynamic binding, it will, when we invoke m, it will call m in the context of class B and the method may fail. So we have actually exceeding time, and we discussed in our 6 hours discussion, we started discussing some very basic concepts on object orientation. We looked at the class diagrams, class relations, how to represent in UML syntax, and then how code is generated for different types of relations among classes. And then we looked at some very basic ideas about UML 2.0 and discussed about the use case modeling for problems. And then today we looked at the sequence modeling, the interaction modeling, and then we tried to develop interaction models for problem, and then try to generate the code from a sequence diagram. And then we looked at a design process and how to the domain model and the sequence diagram which populates the methods, looked at that. And then finally we're looking at the object oriented testing. Unfortunately time is running out. We'll have the slides uploaded. Please read through that, and any difficulty please send me a mail. We'll be happy.